Good afternoon. I'm Jennifer Walker. My company, Watearth, specializes in water resources and green infrastructure, including traditional hydrology, hydraulics, water quality, and also water supply planning. If anybody has questions, I'm happy to answer them at the end of the presentation, or you're also welcome to email me later at jwalker@watearth.com. So today we're going to talk about green woofs and watersheds. So hopefully everybody's here to hear about green infrastructure. So what I've done is I've taken a number of our projects that involve green infrastructure and separated them into redevelopment, new development, and watershed categories. This might be small for those of you at the back. If you'd like copies of these tables, again, feel free to email me. But basically what I did is I listed the largest rainfall event that we analyzed for the project. And you can see the drainage area, you can see the percent of drainage area taken up by the LID features, and then I show the peak flow reduction in that largest event. Some projects were really water quality specific, so we may have only analyzed a 2-year event or even an 85th percentile event. But some projects were related more to flood control, and so they went up to the 100-year, and many of the projects had various components. Just due to space constraints, I'm only listing the largest event for each project. And what's interesting is, so this is primarily projects in the Gulf Coast, so 100-year rainfall events around 12, 13 inches. 10-year, around 10 inches or so. And then there's also a lot of projects in Southern California, so a much more arid environment, but the 100-year may still be 5 inches up to about 7 inches. So the higher end of that extreme is not so different than, like, say, Central Texas, Austin area. And then there's several projects from Northern California in Sacramento and also the Bay Area. So the soils type varies substantially between a lot of clay soils in the Gulf Coast, also in Sacramento, and then some sandier soils within Southern California, but it does vary quite a bit. So in general, we're seeing pretty good peak flow reductions. Now, kind of some conventional wisdom is if it's a high rainfall event, you probably also need a centralized flood control facility. And that's not too far off, but when you have very specific situations, you may be able to manage a very large 100-year event with green infrastructure. Like, for example, I'll show you on a new development slide in a bit. But you can see our peak flow reductions are ranging anywhere from like 25% to 100% on this slide for redevelopment. The 100% means it's essentially 100% infiltration or evapotranspiration, but for the design storm event, it's infiltration. This project's in Southern California in San Bernardino County, so out towards the desert. And it was a very specific grant project that required specific LID areas and contributing areas. So we actually didn't model the entire site. We modeled the area contributing to the LID facilities to show grant compliance. So the reductions are based on that. But essentially for the contributing drainage area, we had 100% infiltration for the 100-year event, which is like 5 or 6 inches. And these features were really, the goal was to treat an 85th percentile event, which it was 1 inch and some change, maybe 1.5 inches. This is also in Southern California in Riverside County, pretty much out in the country in a rural area. For a school district. It's an elementary school retrofit, also a grant project, and the goal was 100% stormwater infiltration from the parking lot and some contributing areas. So we were able to show that for the 100-year 24-hour event and essentially for continuous simulation modeling, so looking at annual events for about a 40-year time period. And it was predominated by porous asphalt, but also some infiltration trenches at the edges. Schools are interesting because there's very specific visibility requirements and safety requirements where the plants that you pick have to be really specific in terms of not too many bees, not too many toxins, so it gets very interesting. And then the rocks in the infiltration trenches had to be quite large so that kids weren't encouraged to pick them up and throw them. And we did build in an overflow into an existing infiltration basin. And in the you know, in the 100-year 24-hour event, it did handle a little bit of a trickle of runoff so that we got complete infiltration. Here's what it looks like, finished product. You've got the solar arrays. So, I mean, in this case, it's not horribly aesthetic because you don't have the bioretention in plants, but that's really what the client wanted, was more of the infiltration trenches. We were able to incorporate some plantings on the edge with a raised berm and some stacked plants to block dust from some nearby agricultural fields. And I'm standing out there to give you a reference of scale. So the big construction issue on this, and we didn't have construction phase services, that was done by the design build firm, but you'll notice they filled the infiltration trenches completely up with rocks, so there should have been a little bit of a like a 6-inch gap there. The performance is still okay, but we would have liked to have seen a little bit of a ponding area. This project's in San Francisco. It's a potential redevelopment project, and the soils vary a little bit between types B, C, maybe a little A and a little D, but they're kind of more moderate soils. And this was a 2-year event to meet combined sewer overflow requirements. So basically just showing that we're meeting specific criteria to achieve like a 25% reduction in runoff volume during a 2-year event of about 2.85 inches. And it looked at things ranging from bioretention, permeable pavement, green roofs because of the high density of where this is, and we also looked at some other things like underground storage. Back to Southern California, this is a medical center master plan, the LAC+USC. It's located near downtown. If you're familiar with Los Angeles, it's really close to Union Station, and it's within the LA River watershed. In this case, very poor soils in terms of infiltration, 0.085 inches per hour, saturated hydraulic conductivity. It's basically a redevelopment of an 84-acre site with permeable pavement, bioretention, and vegetated, or in this case, stormwater wetlands. So you can see they're not, the features, the LID features are not evenly distributed through the site. They're shown in blue and green. So the porous pavement in blue and the bioretention in green. But even so, we were able to demonstrate, as expected, that the runoff is less than existing conditions. And it's not all the way back to undeveloped conditions, but we're well on our way to getting there. So to get back to an undeveloped condition, you'd have to do more retrofit. And then looking at annual events, like the maximum peak discharges on an annual basis. Again, we're somewhere between existing and undeveloped conditions with the blue proposed line. Turning to new development, so we've got mixed use, industrial, and then major thoroughfares. So the major thoroughfares in Houston, again, this is a 100-year event with like 12.4 inches of rainfall. 2 of the 3 drainage areas were treated solely with LID within the median. Now these are rather expanded LID features. It's like a 31-foot median width, and the depth is several feet deep. Although the events did not fill up the swells or the bioretention, that's what was available geometrically. So you can see that the percent peak flow reduction on the new development for the most part isn't ranging quite as high as it is on the redevelopment, because we're comparing to an undeveloped condition. This is one of the major thoroughfares, so it's within a larger industrial district where we're doing a regional master plan for detention and also for a parallel channel and basically like regional detention credits and banking. But over to the right, you can see a roadway that's going in. The soils, clay soils, very low infiltration, but even so, we're able to handle, again, 2 out of 3 of the drainage areas or watershed areas with low impact development. From the topographic map, you can see there's a little steeper area between the western blue line that's a stream at about the middle of the screen. So that's steeper. We weren't able to do bioretention there. We had to do vegetated swells because of the slope. Well, the vegetated swells don't work as well as bioretention for peak flow or runoff reduction because they're more of a conveyance feature. Even though they do slow the water down, they provide some attenuation and lagging of the hydrograph, the bioretention just performs much, much better. So the areas that we were able to fully mitigate with LID were the areas that were flatter where we could get more bioretention in. So on the left-hand side of the screen and then the right-hand side of the screen. Hydrograph comparison from the swells. Here's what the bioretention looks like in terms of filling up for the various events and draining back down. And so you can see in some cases, for some of the events, the bioretention is filling up for the 100-year event. There is an overflow in there. But the vegetated swell is not filling up completely. So on some projects you would optimize and change the geometric configuration. This was kind of set because it's a standard road cross-section. The western portion of it was just separated into a different project. So mostly bioretention, a little bit of swell. Again, these don't fill up completely. Here's what our typical planning level cross sections look like. This has not gone to design yet. And then kind of a conceptual layout with an idea of the plant palette and also street trees. Moving to Southern California, this is right off of the Grand Canal, which is discharges into Ballona Creek and Ballona Lagoon. So it's very sensitive, it's coastal, there's sea level rise issues, tsunami issues. This was part of an environmental impacts report analysis, but very extensive for about a 5,000 square foot site. We actually ended up modeling the site and the Grand Canal watershed for hydrology, low impact development benefits, water quality, and hydraulics within the Grand Canal to show no impact for this. It's an auxiliary pumping plant just to provide capacity to help reduce the likelihood of overflows. And because of liquefaction potential, depth to groundwater, this ended up being like a lined bioretention facility, so we're not really getting infiltration per se. This just shows the basically the surface storage and subsurface or drain rock layer filling up and draining out in the bioretention. So when we look at vector control, requirements vary from location to location, but we're draining out within 72 hours of the start of the event, so that should be in pretty good shape. So we also looked at continuous simulation modeling and things like discharge exceedance frequency curves in terms of hydromodification potential of the stream. So water quality, the line bioretention performed pretty well. There were a couple of pollutants that had very slight increases, so we're recommending some pre-treatment either with a BMP or maybe a sediment trap, filter strip, or so forth. Moving to the Sacramento area, this is a mixed-use development, residential, commercial, open space, roadways, all going in brand new. It is a little bit of a redevelopment because it's currently a gravel mining operation, so there's a lot of regrading of the site that's going to be happening. But primarily we're using bioretention. It's all the turquoise areas and then some larger, more centralized facilities. And here's a conceptual rendering of what the bioretention will look like. And yes, it is poorly draining soil, so an underdrain is definitely required. But when we do the modeling, we use EPA SWIM a lot. We look at the water budget and account for things like, of course, rainfall, but also evapotranspiration if it's a continuous simulation model. We look at storage in the surface layer, infiltration through the growing media, and percolation into the native soil, as well as any overflow, runoff through an underdrain if it exists, and also run-on into the LID feature. So we show good performance on an annual basis. But that project was primarily driven by the desire to reduce the size of the storm drain system, which the LID has been able to do effectively. And then I have 3 projects in here that look at more watershed type benefits. And one is in the San Francisco Bay Area in Sonoma. So it's a little bit more of an undeveloped watershed. One's in Houston within urban watershed, and then one's in Fort Worth within a very urban watershed. And all of them show peak flow reductions, but the amount of the reduction basically varies based on the extent of the LID features. So we have some that are up at the 97% range on the very lower one, but the LID is 27% of the drainage area. And then you have some at the very lower end, like 2% reduction, but the LID is only 2% of the drainage area. So really, when we talk about watershed benefits, it's how much LID can you, or green infrastructure can you incorporate into the watershed. We can also get into cost optimization of where to place it within the watershed. Some of the work we're doing with the San Francisco Estuary Institute on San Francisco Bay Area green infrastructure planning and master plans really starts to look at watershed type placement. And if you're interested in that, we have a short YouTube video on this particular project. But we first did like a GIS screening to identify locations that would be basically ideal spots for bioretention, permeable pavement, and some other LID features within the watershed. And initially the tool included bioretention, wet ponds, and stormwater wetlands. We've since gone through several rounds of grant funding and have added in numerous other features, including like tree boxes, lined bioretention, vegetated swells, infiltration trenches, and so forth. And what we found in Dowdle Creek watershed was a good reduction for this undeveloped watershed. But we really, if we treated the undeveloped watershed as if it were developed and just simply increased the impervious cover to 60%. We didn't mess with times of concentration or anything like that. We just changed the impervious cover, and we found that it substantially increased the reduction in peak discharge for these events. So the 10-year was about a 7-inch event. So it went for undeveloped, it went from 29%, same amount of LID, but we considered it to be a developed watershed, 52% reduction. This is within the city of Fort Worth, Zoo Creek watershed. It's very centrally located. And so planning level effort where we did LID modeling in SWIM, quantified reductions in runoff, and then took those hydrographs and imported them. So first the hydrographs were exported from Innovi's ICM. The LID modeling was done in SWIM, and then we imported the hydrographs from the LID modeling back into the ICM model to be able to show changes in the floodplain within the watershed by incorporating LID as laid out in a planning study. So you can see it's about a 9-inch event for the 100-year event. And the percent of the drainage area for the LID features just varies based on the drainage area. I do want to talk a little bit, and Carrie touched on operations and maintenance. I think that's really, really critical. So we've got almost like 3 legs of a triangle or a stool. We need really good design, we need good construction, but we also need good operations and maintenance for these features to perform long term. One of the things I like about green infrastructure is even without maintenance, it will tend to continue performing, but the maintenance is really critical in terms of sustainability and resilience. Envision certification on projects, it does have points for O&M planning. This is for a operations and maintenance manual we did for City of Santa Monica, which they have a lot of BMPs for a small city, really, really progressive. This is kind of a customized one with underground storage and infiltration. and then a manufactured dry well that's also used for infiltration. At the Riverside County Flood Control and Water Conservation District, interpretive signage. They actually have a brochure that we developed for them and a walking tour so that their staff can enjoy the retrofit at the site, but visitors can also learn as they walk through the site, read the interpretive signage, and read the brochure. So many projects that we work on that have grants require this type of educational outreach, but even if it's not required, it's a really good way to reach residents and citizens and the general public as well as elected officials on educating them more about stormwater and flood control and water quality. And then that can be targeted. This is for more of a kid's site on rain gardens. And this is at the elementary school with the parking lot that's 100% infiltration. So it's very much targeted towards elementary students, but in the lower right-hand corner you can see that we have a segment on maintenance. So as maintenance staff turns over, hopefully people down the line will read it and say, oh, hey, we're supposed to do this with the porous pavement or with the infiltration trenches. So a few final thoughts. If you have follow-up for me, you're welcome to email me at jwalker@watearth.com. All right, thank you. I appreciate it.